Welcome students, I am Dr. Rajesh Singh and in this video we will solve exercise 5.1 from the book Bartle and Sherbert. So let us start with question number 1. In question number 1 we have to prove the sequential criterion which is given in 5.1.3, so which is this. A function f from a to r is continuous at a point c belonging to a if and only if for every sequence xn in a that converges to C, the sequence fxn must converge to fc. So for this, let us start. Solution. So we will assume that f is continuous at C belonging to A, and we will show that for every sequence xn in A that converges to C, the corresponding sequence fxn must converge to fc. So let xn be any sequence in A converging to C. To show f of xn converges to fc. So for this, what we will do? So we will use the continuity of f at C. Let epsilon greater than 0 be any real number. So we have to find m belonging to z positive such that what will happen? fx n minus fc is less than epsilon for all n greater than equal to m. So this is what we have to show. So we have to find some m belonging to z positive such that fxn minus fc is less than epsilon for all n greater than equal to m. So for this, what we will use the continuity of f at C. F is continuous at C belonging to A. So for above epsilon greater than 0, there exists delta greater than 0 such that x minus c less than delta implies fx minus fc is less than epsilon. So mark this as A. Now as xn converges to C, so for above delta greater than 0, so instead of epsilon we are taking delta. So for this delta greater than 0, there exists m belonging to z positive such that xn minus c is less than delta for all n greater than equal to m. So this is B. So consider for all n greater than equal to n, then xn minus c is less than delta using A, using B, and xn minus c less than delta implies fxn minus fc is less than epsilon using A. So this follows from A. Hence fxn minus fc is less than epsilon for all n greater than equal to m, that is fxn converges to fc. So one way we have proved. Conversely, so we assume that for every sequence xn in A converging to C, the sequence fxn converges to fc. So to show f is continuous at C, so suppose on the contrary f is not continuous at C. So if f is not continuous at C, then we will negate the definition of continuity. So there exists epsilon greater than 0 such that for each delta greater than 0 there exists x depending on this delta. So I will mark x delta belonging to A such that fx delta minus fc is greater than epsilon, but x delta minus c is less than delta. So x delta minus c is less than delta, but fx delta minus fc is greater than epsilon. So mark this as, so this is negating the definition of continuity, because in continuity we have for each epsilon greater than 0 there exists delta greater than 0, such that for every x in A with x minus c less than delta, fx minus fc should be less than epsilon. So negating that, we get there exists epsilon greater than 0, such that for each delta there exists x delta belonging to A such that fx delta minus fc is greater than epsilon. So now, since the statement is true for every delta, so what we will do, we will take delta equal to 1, delta equal to 1 by 2, delta equal to 1 by 3, delta equal to 1 by 4 and so on, and correspondingly we will get x1, x2, x3, x4 such that fx1 minus fc is greater than 1, so this way. So in particular, for each n belonging to n, delta n equal to 1 by n, there exists xn belonging to A such that xn minus c is less than 1 by n and fxn minus fc is greater than epsilon. So thus, now xn minus c is less than 1 by n for all n belonging to n. So now, since xn minus c is less than 1 by n for all n belonging to n, so this implies xn converges to c. But as fxn minus fc is greater than epsilon for all n belonging to n, so this implies fxn does not converge to fc. So we have found a sequence xn that converges to c such that the corresponding sequence fxn does not converge to c, which is a contradiction which contradicts the hypothesis. Hypothesis is that for every sequence xn in A that converges to c, the corresponding sequence must converge to fc, but we have constructed a sequence xn that converges to c such that the corresponding sequence is not converging to fc. So hence our assumption is wrong and f is continuous at c belonging to A. So this completes the proof of question number 1. Now let us move to question number 2. In question number 2, we have to establish the discontinuity criteria. So what is the discontinuity criteria? So discontinuity criteria is that if f is discontinuous at c, if and only if there exists a sequence xn in A such that xn converges to c but the corresponding sequence fxn does not converge to fc. So this is similar to what we did in the converse part of the last theorem. So you just have to rewrite the proof of last theorem and you will get the proof of this theorem. Solution: simply rewrite proof of last question. Fine. So I am not going to prove this. You can just, because if you will assume that f is discontinuous at c, then c. In this case, I have assumed that f is not continuous at c, and I have been able to construct a sequence xn that converges to c, but the corresponding sequence fxn is not converging to fc. Conversely, on the contrary, you can assume that f is continuous at c, and then you will be able to contradict this statement. We just have to rewrite the proof of last question, so I am not going to prove this question in this video. So let us move to question number 3. So in question number 3, we have been given that f is continuous on AB, G is continuous on BC, such that FB is equal to GB. We define H on AC by Hx equal to Fx for x belonging to AB and Hx equal to Gx for x belonging to BC. We have to prove that H is continuous on AC. So let us start with the solution. We are given F is continuous on AB, G is continuous on BC, and FB is equal to GB. H is defined from AC to R as Hx equal to Fx if x belongs to AB, and it is Gx if x belongs to BC. So to show H is continuous on AC, so we will do this in 3 cases. So we will let P belonging to AC be any point. So we will show that H is continuous at P. So for this, what we will do, let epsilon greater than 0 be any real number. So to find delta greater than 0 such that x minus c is less than delta implies Hx minus Hp is less than epsilon. So this is what we have to show. So we will prove this in 3 cases. We will take the case 1 when P is less than B. So when P is less than B, so this is the first case. So since F is continuous at P because P belongs to the interval AB, so F is continuous at P. So for above epsilon greater than 0, there exists delta 1 greater than 0 such that x minus p is less than delta 1 implies fx minus fp is less than epsilon, and here x belongs to AB. So x minus p is less than delta 1 and x belongs to AB, so this implies fx minus fp is less than epsilon. Now let delta equal to minimum of delta 1 and b minus p by 2. So this I have taken delta equal to minimum of delta 1 and b minus p by 2. So why I have done this? Because suppose this is my A, this is B and this is C. So P is somewhere here. Now in this case I have been given that if x minus p is less than delta 1, so delta 1 could be this also. So x minus delta 1 could be this also. So what I want the interval to be around this only, so that fx and hx should be equal. So and I have to remove this extra condition, so that's why I have taken my delta like this. Yes. So now, for this delta, x minus p less than delta and x belonging to AC implies x minus p is less than delta 1 because delta is less than delta 1, and because of this condition that delta is less than b minus p by 2, so x belongs to AB, and from star, so mark this as star, so from star this implies fx minus fp is less than epsilon from star, and x belongs to AB. So this implies hx minus hp is less than epsilon. Thus x for delta equal to minimum of delta 1 and b minus p by 2, x minus p less than delta and x belonging to AC implies hx minus hp is less than epsilon. So that is h is continuous at p. So in this case we have shown that h is continuous at p. Now case 2, if p is greater than b. So in this case again as g is continuous at p, so for above epsilon greater than 0 there exists delta 2 greater than 0 such that x minus p less than delta 2 and x belonging to BC implies gx minus gp is less than epsilon. So mark this as double star. This, so what we will do, we will take let delta equal to minimum of delta 2 and p minus p by 2. So then for this delta, obviously if I take x minus p less than delta and x belonging to AC, then this implies x minus p is less than delta 2 because this delta is less than delta 2, and x belongs to BC because x belongs to AC and x minus p less than delta and delta is less than p minus b by 2 implies x belongs to BC. And then from double star we have gx minus gp is less than epsilon from double star, and since our x belongs to BC, so this implies gx is equal to this and this is hp is less than epsilon. So thus x minus p less than delta and x belonging to AC implies hx minus hp is less than epsilon. So for this is true for delta equal to minimum of delta 2 and p minus b by 2. So this thus h is continuous at p. So this completes case 2. Now case 3, when p is equal to b. So then in this case both f and g are continuous at p. So for epsilon greater than 0 there exists delta 3, delta 4 greater than 0. So for this f delta 3 is there and for g there is delta 4 such that x minus p less than delta 3 and x belonging to AB implies fx minus fp is less than epsilon. So this is our A, and x minus p less than delta 4 and x belonging to BC implies gx minus gp is less than epsilon. So this is our B. So what we will do, we will take delta equal to minimum of delta 3 and delta 4. So let delta equal to minimum of delta 3, delta 4. So then for this delta, so consider for x such that x minus p is less than delta and x belongs to AC. So I am starting with hx minus hp. So this I can write as equal to, so hp is equal to fp as well as gb. So this I can write as fx minus fp if x belongs to AB and gx minus gp if x belongs to BC. And what does this imply? So both are less than epsilon whenever x minus p is less than delta. So this is less than epsilon. So both are less than epsilon. So this is less than epsilon. Hence, for delta equal to minimum of delta 3, delta 4, x minus p less than delta and x belonging to AC implies hx minus hp is less than epsilon. Hence, h is continuous at P. So in all the three cases we have shown that H is continuous at P. So this completes the proof of question number 3.